Hey, this is Warner, and this is the 2003 number 2 Mechanics AP Physics C exam, and we are going to take a look at this very first problem. This is actually number 2. In this one, we have an ideal spring. There it is, hung from the ceiling, and a pan of mass M is suspended from the end of the spring. So there it is. Oops, sorry, here is the pan. It's got a big mass M. Stretching at a distance of d, a piece of clay also of mass m, so notice they both have the same mass, is then dropped from a height h, and that falls down and it sticks to the pan. They want us to make sure we express all algebraic answers in terms of the given quantities and fundamental constants. Determine the speed of the clay at the instant it hits the pan. So this is pretty easy to do. You can do it one of two ways. You can either do it using energy, which I would do, or you can use kinematics. So totally up to you either way you want to do it. So what we'll do is we know that right off the bat the clay has potential energy equal to mg times h. That's equal to 1/2 of the mass of the clay times the speed of the clay squared. So let's go ahead and solve this for the speed of the clay. So that would be the speed of the clay is equal to, notice that your masses will cross off on both sides because they are both the same thing. And now we are left with the square root of 2 times g times the height. And that is it. That is where those 2 points come from. For letter B, determine the speed of the pan just after the clay strikes it. So here we know that the momentum has got to be conserved. And so we will have big M times the velocity of the clay should be equal to the mass of the pan plus the mass of the clay, and because they have the same mass we can do that, and then that is times the velocity of the pan and the mass. So our final velocity of the pan, because the mass is stuck to it and they're going to have the same velocity, is equal to, and then here we're going to say 1/2 of the square root of 2 times g times h. Because remember earlier we said that the velocity cvc is equal to the square root of 2gh. Where did the half come from? This really is also equal to 2m times vp, so that's where that came from. That would be a three-pointer. This shows that it is inelastic. The other thing you could do is just say it's an inelastic collision. So you get 1 point for just recognizing that it is inelastic collision. You get 1 point for this equation, and you get 1 point for solving for the velocity. So far pretty easy problem to do. Next thing they want us to do is determine the period of the simple harmonic motion that results. So to do that, we just need to remember our equation. Actually, it's on the equation sheet. T is equal, this is period of a spring, T is equal to 2 pi times the square root of the mass divided by the spring constant. We know that this m, so we know that the mass is equal to 2 times big M. And now we can say that the mass times gravity is equal to k times d. So remember, this is force is equal to k times x. So those are the same thing. This is the force on the spring. This is the spring constant, and then d is our stretch. And because we have this now, we can solve for k. So k is equal to big M times g all over that displacement. And now we're going to substitute everything in. So notice now we've got t is equal to 2 pi times the square root of 2d over g. And so that is worth 4 points. You get 1 point for the original equation, you get 1 point for this, you get 1 point for solving for k, and then for plugging that k in, the m over k. And when you do that, you get rid of the m, obviously, and the d becomes 2d, and then that is over g. So now we are set This is 1, 2, 3, and then finally the fourth point. The very last thing that they want us to do here, second to last, sorry, is determine the distance that the spring is stretched from its initial, you have to be careful, initial unstretched length. At the moment, the speed of the pan is a maximum, and then they want us to justify our answer. So our speed, you know, is a maximum at the equilibrium point. So the Vmax should be at equilibrium. Equilibrium is where sum of your forces is equal to 0. So the sum of the forces is equal to 0. That is where A, acceleration, is equal to 0. Your kinetic energy is equal to a maximum. Any of those things you could say. So the second thing that we need to do here is recognize that there's a new equilibrium point. So this was one point. The next point is there is a new equilibrium point. So there is a new equilibrium point, and that is at, we're going to use the equation kx is equal to 2 times mg, where x here is the distance that the spring is stretched from its initial unstretched length. So now we're going to substitute in that value of k that we had on the previous part. So remember, k is equal to mg over d. So we're going to put mg over d times x, and then that is equal to 2 times m times g. And we can go through and cross off our m's, cross off the g's. Oops, sorry, I want to leave that 2 there. So that 2 stays. The m gets crossed off, sorry. And now we have x is equal to, multiply both sides by d, and that would be 2d. So your correct answer here is x is equal to td, and you get that point, and so that would give you all 3 points. For letter E, it says the clay is now removed from the pan and the pan returned to equilibrium at the end of the spring. A rubber ball of mass m is dropped from the same height, and after collision, it is caught in midair before it hits anything else. They want us to indicate below whether your period of the resulting simple harmonic motion of the pan is greater than, less than, or the same thing that it was in part C. And for this one, if you think about it, it should be less than. Now, why is the period less than? It is because in the second case, there is less mass oscillating. And because there is less mass oscillating than in part C, we know that we can use the equation t is equal to 2 pi times the square root of m over k. If there's less mass, then you will have a period that would be shorter. K is going to stay the same, 2 pi is going to stay the same, but because you have less mass oscillating, then the period will decrease. Period will decrease is what you need to write. The equation here, you don't have to, it's really not needed. And that is the end of the problem.